Natural language processing, NLP. NLP is a field of artificial intelligence focused on the interaction between computers and humans through natural language. It involves the development of algorithms and models to process and understand human language. It works by including tasks such as text classification, sentiment analysis, machine translation, and question answering. For example, virtual assistants like Siri and Alexa use NLP to understand and respond to user queries. Research on this topic can be found in Survey of the State of the Art in Natural Language Processing by Manning et al., 2015.
Like, comment, and subscribe.
Language models. Language models are computational models designed to predict the probability of a sequence of words. They are used to generate text, understand context, and perform various NLP tasks. They work by learning from large corpora of text to understand language patterns. For instance, language models like GPT-3 generate coherent and contextually relevant text based on a given prompt. A detailed study is presented in A Neural Probabilistic Language Model by Bengio et al., 2003.
Like, comment, and subscribe.
Large language models. LLMs, advanced language models with billions of parameters, trained on extensive datasets to understand and generate human-like text. They work by leveraging deep learning techniques and vast amounts of data to achieve high performance in various NLP tasks. An example of this is GPT-3, which, with 175 billion parameters, can perform tasks such as translation, summarization, and question answering. The strengths of LLMs include their high performance across a wide range of tasks and their ability to generate highly coherent and contextually accurate text. However, they require significant computational resources for training and inference, and have the potential for generating biased or inappropriate content. This concept is thoroughly explored in Language Models Are Few-Shot Learners by Brown et al., 2020.
Like, comment, and subscribe.
Pre-trained models. Pre-trained models are models that have been previously trained on a large dataset and can be fine-tuned for specific tasks. They work by leveraging transfer learning to adapt to new tasks with minimal additional training. For example, BERT is pre-trained on masked language modeling and next sentence prediction tasks, then fine-tuned for specific NLP tasks. The strengths of pre-trained models include saving time and computational resources in training models from scratch, and often achieving higher performance on specific tasks with less training data. However, they may require extensive fine-tuning for domain-specific tasks, and pre-training data biases can transfer to the fine-tuned model. A foundational paper on this is BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding, by Devlin et al., 2018.
Like, comment, and subscribe.
Transformers. Transformers are neural network architectures that enable parallel processing of sequences for efficient language understanding and generation. They work by using self-attention mechanisms to focus on different parts of the input data, allowing for better context understanding and high-quality text outputs. The foundational transformer model introduced by Vaswani et al. In Attention is All You Need, 2017, powers popular LLMs like BERT and GPT. The strengths of transformers include efficient parallel processing and effective handling of long-range dependencies. However, they have high computational and memory requirements. This concept is discussed in Attention is All You Need by Vaswani et al., 2017.
Like, comment, and subscribe.
Encoder-decoder architecture. The encoder-decoder architecture uses an encoder to process the input sequence and a decoder to generate the output sequence. It works by having the encoder convert the input sequence into a fixed-size context vector, which is then used by the decoder to produce the output. This architecture is used in sequence-to-sequence models like machine translation. And its strengths include being effective for tasks involving input-output sequence transformations. Its weaknesses include struggling with very long input sequences. This concept is detailed in Sequence-to-Sequence Learning with Neural Networks by Sutskever et al., 2014.
Like, comment, and subscribe.
Recurrent neural networks, RNNs. Recurrent neural networks, RNNs are designed to handle sequential data by maintaining a hidden state that captures information about previous inputs. They work by processing sequences of data one element at a time, updating their hidden state at each step. An example of RNNs includes long short-term memory, LSTM networks, that mitigate the vanishing gradient problem with gating mechanisms. The strengths of RNNs are their effectiveness for handling sequential data and maintaining context. Their weaknesses include struggling with long-range dependencies and being less efficient compared to transformers. A seminal paper on RNNs is Long Short-Term Memory by Hochreiter and Schmidhuber, 1997.
Like, comment, and subscribe.
Dynamic Memory Networks, DMNs. Dynamic Memory Networks, DMNs, are neural networks designed to answer questions based on dynamic memory updates. They work by involving modules for input, question understanding, episodic memory, and answer generation, allowing iterative reasoning about input data. DMNs are used in tasks requiring complex reasoning and understanding, such as narrative comprehension. The strengths of DMNs include being effective for tasks requiring multi-step reasoning. Their weaknesses include having a complex architecture and higher computational requirements. This concept is explored in Dynamic Memory Networks for Visual and Textual Question Answering by Kumar et al., 2016.
Like, comment, and subscribe.
Attention mechanisms. Attention mechanisms assign different weights to input tokens, highlighting the most relevant parts of the text for processing. They work by including variants like self-attention within the same sequence and cross-attention between sequences, such as in encoder-decoder models. For example, transformers use multi-head self-attention to manage long-range dependencies in text, which is crucial for tasks like translation and summarization. The strengths of attention mechanisms include allowing models to focus on important parts of the input, handling long dependencies effectively. Their weaknesses are that they are computationally intensive. This concept is thoroughly discussed in Attention is All You Need by Vaswani et al., 2017.
Like, comment, and subscribe.
Self-attention. Self-attention mechanisms focus on different parts of the same input sequence to compute a representation of the sequence. They work by having each token in the sequence attend to all other tokens, allowing the model to capture relationships between tokens. Self-attention is used in transformers to process input sequences in parallel. The strengths of self-attention include enabling efficient parallel processing and capturing global dependencies. Its weaknesses include requiring significant computational resources. This concept is detailed in Attention is All You Need by Vaswani et al., 2017.
Like, comment, and subscribe.
Multi-head attention. Multi-head attention uses multiple attention mechanisms in parallel to capture different aspects of relationships between tokens. It works by having each head perform self-attention independently, and their outputs are concatenated and transformed to produce the final output. For example, it enhances the model's ability to focus on various parts of the input sequence simultaneously. The strengths include improving the capacity to capture diverse relationships in data. The weaknesses include adding to the model's complexity and computational requirements. This concept is discussed in Attention is All You Need by Vaswani et al., 2017.
Like, comment, and subscribe.
Cross-attention. Cross-attention allows models to focus on different parts of input sequences by attending to segments from other sequences. It works by being common in encoder-decoder architectures, enhancing context understanding. For example, transformers like T5 use cross-attention to improve translation and summarization. The strengths include enabling effective input-output sequence transformations. The weaknesses include increasing computational requirements. This concept is explored in Exploring the Limits of Transfer Learning with a Unified Text-to-Text Transformer by Raffel et al.
Like, comment, and subscribe.
Sparse attention. Sparse attention mechanisms optimize the efficiency of attention computations by focusing on relevant parts of the input sequence, reducing computational load. They work by being essential for handling longer sequences without excessive resource use. For example, models like Longformer and Big Bird use sparse attention to manage long documents effectively. The strengths include efficient handling of long sequences and reduced computational cost. The weaknesses include potentially losing some information due to sparsity. This concept is detailed in Longformer, the Long Document Transformer by Beltegi et al., 2020.
Like, comment, and subscribe.
Positional encoding. Positional encoding is a technique used in transformer models to incorporate information about the positions of tokens in a sequence. It works by adding sine and cosine functions of different frequencies to token embeddings, providing a unique representation for each position. For example, positional encoding allows transformers to process sequences in parallel while retaining order information. The strengths include enabling transformers to handle sequential data efficiently. The weaknesses include fixed encoding potentially not capturing all positional nuances. This concept is discussed in Attention is All You Need by Vaswani et al., 2017.
Like, comment, and subscribe.
Contextual word embeddings. Contextual word embeddings are dynamic representations of words that change based on surrounding context, capturing the nuances of word meanings. They work by adjusting word vectors depending on their context in a sentence. For example, Elmo and Bert provide contextual word embeddings that improve the performance of downstream NLP tasks. The strengths include capturing rich semantic information, improving task performance. The weaknesses include being computationally intensive to generate and store. This concept is detailed in Deep Contextualized Word Representations by Peters et al., 2018.
Like, comment, and subscribe.
Word embeddings. Word embeddings are dense vector representations of words that capture their meanings and relationships based on context. They work by using techniques like Word2Vec and Glove to learn from large text corpora to place words in a continuous vector space. For example, Word2Vec predicts context words surrounding a target word, skipgram model. The strengths include capturing semantic similarities between words. The weaknesses include static embeddings not adapting to different contexts. This concept is explored in Efficient Estimation of Word Representations in Vector Space by Mikolov et al., 2013.
Like, comment, and subscribe.
Bidirectional encoder representations. Bidirectional encoder representations are models that process text in both forward and backward directions, capturing context from both sides of a token. They work by learning to predict tokens using information from both preceding and following tokens in the sequence. For example, BERT is a prime example, achieving state-of-the-art performance in various NLP tasks. The strengths include providing rich contextual understanding by looking at the full context. The weaknesses include being more computationally expensive than unidirectional models. This concept is discussed in BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding by Devlin et al., 2018.
Like, comment, and subscribe.
BERT, Bidirectional Encoder Representations from Transformers. BERT is a pre-trained transformer model designed to understand bidirectional context in sentences. It works by using masked language modeling, randomly masking words in a sentence and predicting them based on context. For example, BERT can be fine-tuned for text classification, question answering, and more. The strengths include strong performance on a variety of NLP tasks and capturing rich contextual information. The weaknesses include being computationally intensive and requiring large datasets for pre-training. This concept is detailed in BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding by Devlin et al., 2018.
Like, comment, and subscribe.
GPT, Generative Pre-Trained Transformer. GPT is a series of autoregressive language models developed by OpenAI, pre-trained to generate text by predicting the next word in a sequence. It works by being trained using a language modeling objective, learning to generate text by predicting the next word based on previous words. For example, GPT-3 can generate highly coherent and contextually relevant text based on a given prompt. The strengths include excellent text generation capabilities, adaptable to various tasks. The weaknesses include high computational requirements and the potential for generating biased content. This concept is explored in Language Models Are Few-Shot Learners by Brown et al., 2020.
Like, comment, and subscribe.
Autoregressive models. Autoregressive models predict the next token in a sequence based on previous tokens. They work by generating text one token at a time, conditioning each prediction on previously generated tokens. For example, GPT-3 uses autoregressive modeling to generate coherent text based on a given prompt. The strengths include the ability to generate high-quality text with coherence and fluency. The weaknesses include potentially suffering from exposure bias, where errors accumulate as more tokens are generated. This concept is discussed in Improving Language Understanding by Generative Pre-Training by Radford et al., 2018.
Like, comment, and subscribe.
Fine-tuning. Fine-tuning involves adapting a pre-trained model to specific tasks using additional training on task-specific data. It works by adjusting the model's weights based on new data to improve performance on the target task. For example, fine-tuning BERT for sentiment analysis. The strengths include efficiently leveraging pre-trained knowledge, reducing the need for large task-specific datasets. The weaknesses include the potential need for careful tuning of hyperparameters to avoid overfitting. This concept is discussed in BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding by Devlin et al., 2018.
Like, comment, and subscribe.
Transfer learning. Transfer learning leverages knowledge from one task to improve performance on another, related task. It works by using a pre-trained model as a starting point and fine-tuning it on a new task. For example, fine-tuning GPT-3 for specific tasks like translation, benefiting from pre-trained language understanding. The strengths include reducing data and computational requirements for training models on new tasks. The weaknesses include the potential for the pre-trained model's biases to affect performance on new tasks. This concept is explored in A Survey on Transfer Learning by Pan and Yang, 2010.
Like, comment, and subscribe.
Efficient fine-tuning. Efficient fine-tuning involves techniques like low-rank adaptation, LoRa for task-specific adaptation with reduced computational cost. It works by introducing low-rank updates to model parameters, reducing memory usage and cost. For example, LoRa fine-tuning GPT-3 for domain-specific applications, enhancing efficiency while maintaining performance. The strengths include reducing computational and memory requirements, making fine-tuning feasible on limited resources. The weaknesses include the possibility of not achieving the same level of performance as full fine-tuning. This concept is discussed in Low-Rank Adaptation of Large Language Models by Hu et al., 2021.
Like, comment, and subscribe.
Multitask learning. Multitask learning involves training models to perform multiple tasks simultaneously, leveraging shared representations. It works by improving model efficiency and performance by learning from diverse tasks. For example, Unified QA model trained on various QA datasets to enhance generalization. The strengths include efficient use of resources and potential for improved generalization. The weaknesses include the potential need for careful balancing of tasks to avoid performance degradation. This concept is explored in an overview of multitask learning in deep neural networks by Reuter, 2017.
Like, comment, and subscribe.
Self-supervised learning. Self-supervised learning is a training approach where the model learns from the inherent structure of the data without requiring labeled examples. It works by having models generate their own labels from the data by solving tasks like predicting masked words. For example, BERT uses self-supervised learning to predict masked tokens during pre-training. The strengths include efficiently utilizing large unlabeled datasets and reducing dependency on labeled data. The weaknesses include the possibility of self-generated labels introducing noise, requiring careful task design. This concept is discussed in Self-Supervised Learning, The Dark Matter of Intelligence by LeCun, 2020.
Like, comment, and subscribe.
Zero-shot learning. Zero-shot learning enables models to perform tasks with no examples during training. It works by leveraging knowledge from related tasks or general language understanding to make predictions. For example, GPT-3 performs zero-shot learning, generating accurate outputs based on prompts without prior task-specific training data. The strengths include high flexibility and the ability to handle novel tasks without additional training. The weaknesses include potentially lower performance compared to fine-tuned models on specific tasks. This concept is discussed in Zero-Shot Learning, a comprehensive evaluation of the good, the bad, and the ugly, by Xian et al., 2017.
Like, comment, and subscribe.
Few-shot learning. Few-shot learning enables models to perform tasks with very few examples during training. It works by using a small number of labeled examples to adapt pre-trained models to new tasks. For example, GPT-3 demonstrates few-shot learning by adapting to tasks with minimal examples provided in the prompt. The strengths include reducing the need for large labeled datasets and enabling quick adaptation. The weaknesses include the need for careful selection of examples and possibly not achieving the highest performance. This concept is explored in Language Models Are Few-Shot Learners by Brown et al., 2020.
Like, comment, and subscribe.
Meta-learning. Meta-learning, or learning to learn, involves models quickly adapting to new tasks using small amounts of data. It works by training a model on a variety of tasks to learn underlying patterns of task adaptation. For example, meta-learning is used in models like MAML to improve the speed and efficiency of learning new tasks. The strengths include high adaptability and efficient learning from few examples. The weaknesses include being computationally intensive and having complex training procedures. This concept is discussed in Model-Agnostic Meta-Learning for Fast Adaptation of Deep Networks by Finn et al., 2017.
Like, comment, and subscribe.
Federated learning. Federated learning allows training models across decentralized devices or servers holding local data samples without exchanging them. It works by aggregating updates from local models to create a global model while keeping the data localized. For example, federated learning is used in applications like Google's Gboard to improve text prediction without sharing user data. The strengths include enhancing privacy and reducing data transfer. The weaknesses include the need for robust mechanisms for model update aggregation and handling non-IID data. This concept is discussed in Communication-Efficient Learning of Deep Networks from Decentralized Data by McMahon et al., 2017.
Like, comment, and subscribe.
Masked Language Modeling, MLM. Masked Language Modeling, MLM, is a pre-training objective where random tokens in a sequence are masked and the model learns to predict the masked tokens. It works by training models to understand bidirectional context by predicting masked words based on surrounding context. For example, BERT uses MLM to capture deep contextual information from text. The strengths include capturing rich bidirectional context and improving understanding of text. The weaknesses include requiring large datasets and extensive training. This concept is discussed in BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding, by Devlin et al., 2018.
Like, comment, and subscribe.
Next Sentence Prediction, NSP. Next Sentence Prediction, NSP, is a pre-training objective used in models like BERT to understand the relationship between pairs of sentences. It works by training the model to predict whether a given sentence follows another in a coherent text. For example, NSP helps models understand and capture discourse-level relationships. The strengths include enhancing models' ability to understand sentence-level coherence. The weaknesses include it may not be effective for all types of textual relationships. This concept is discussed in BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding by Devlin et al., 2018.
Like, comment, and subscribe.
Tokenization. Tokenization is the process of breaking down text into smaller units called tokens, which can be words, subwords, or characters. It works by utilizing effective tokenization methods like byte pair encoding, BPE, and word piece tokenization, which are crucial for LLM performance. For example, tokenization allows models to handle diverse languages and complex vocabulary efficiently, as seen in models like Bloom and GPT-3. This concept is explored in Neural Machine Translation of Rare Words with Subword Units by Senric et al., 2016.
Like, comment, and subscribe.
Sequence of words. A sequence of words is an ordered list of words that forms a sentence or a phrase, representing the textual input used for processing in natural language tasks. It works by tokenizing and processing these sequences to understand context and meaning. For example, a simple sequence could be, "The quick brown fox jumps over the lazy dog." This is a general concept in NLP without a specific research paper.
Like, comment, and subscribe.
Layer normalization. Layer normalization is a technique to normalize the inputs to each layer, improving training stability and performance. It works by normalizing inputs based on the mean and variance of the current batch. For example, it is used in transformers like BERT and GPT for stable and accelerated training. The strengths include improving training stability and accelerating convergence. The weaknesses include additional computational overhead. This concept is discussed in Layer Normalization by Bo et al., 2016.
Like, comment, and subscribe.
Distributed training. Distributed training involves training large models across multiple GPUs or machines to reduce training time and handle larger models. It works by using techniques such as data parallelism and model parallelism for efficient training. For example, distributed training is used by OpenAI and Google for training models like GPT-3 and BERT. The strengths include enabling handling of extensive datasets and complex models and reducing training time. The weaknesses include requiring sophisticated infrastructure and synchronization mechanisms. This concept is discussed in large-scale distributed neural network training through online distillation by Anil et al., 2018.
Like, comment, and subscribe.
Model compression. Model compression involves techniques to reduce the size of neural networks while maintaining performance, making them more efficient for deployment. It works by employing methods such as pruning, quantization, and knowledge distillation. For example, DistillBERT is a smaller version of BERT that retains high performance with fewer parameters. The strengths include reducing model size, improving inference speed, and reducing resource requirements. The weaknesses include possibly losing some accuracy compared to the original model. This concept is discussed in DistillBERT, a distilled version of BERT, smaller, faster, cheaper, and lighter, by San et al., 2019.
Like, comment, and subscribe.
Model pruning and quantization. Model pruning and quantization are techniques to reduce the size and improve the efficiency of LLMs without significantly compromising performance. It works by pruning, which removes less important neurons or weights, while quantization reduces the precision of the model weights. For example, these techniques are applied to large models like GPT-3 to make them more suitable for deployment on devices with limited computational resources. The strengths include significantly reducing model size and inference time. The weaknesses include possibly requiring fine-tuning to recover performance. This concept is explored in Quantizing Deep Convolutional Networks for Efficient Inference by Corbario et al., 2016.
Like, comment, and subscribe.
Memory augmentation. Memory augmentation involves incorporating external memory mechanisms to enhance LLM's ability to recall and use information from past interactions. It works by improving contextual understanding and response consistency over long-term interactions. For example, models like GPT-4 incorporate memory augmentation to handle complex, context-rich interactions. The strengths include enhancing long-term context understanding and improving interactive capabilities. The weaknesses include adding complexity to model architecture and training. This concept is discussed in Improving Language Models by Retrieving from Trillions of Tokens by Borgo et al., 2021.
Like, comment, and subscribe.
Knowledge distillation. Knowledge distillation involves training a smaller model, student, to replicate the behavior of a larger pre-trained model, teacher. It works by creating efficient models that retain the performance of larger models with fewer computational resources. For example, DistilBERT is a distilled version of BERT with fewer parameters and faster inference times. The strengths include reducing model size and resource requirements while maintaining performance. The weaknesses include possibly losing some accuracy compared to the original large model. This concept is discussed in DistilBERT, a distilled version of BERT, smaller, faster, cheaper, and lighter, by Sand et al., 2019.
Like, comment, and subscribe.
Retrieval Augmented Generation. Retrieval Augmented Generation, RAG, combines retrieval-based and generation-based approaches to improve the quality of generated text by incorporating relevant external information. It works by retrieving relevant documents or information during the text generation process to provide contextually accurate and detailed responses. For example, RAG models can answer complex questions by retrieving and generating answers from a large corpus. The strengths include providing accurate and context-rich responses by leveraging external knowledge bases. The weaknesses include requiring efficient retrieval mechanisms and adding complexity to the model. This concept is discussed in Retrieval Augmented Generation for Knowledge-Intensive NLP Tasks by Lewis et al., 2020.
Like, comment, and subscribe.
Prompt engineering. Prompt engineering involves designing and optimizing input prompts to elicit desired responses from LLMs. It works by improving the quality of generated outputs, making the model more useful for specific tasks. For example, using carefully crafted prompts, GPT-3 can generate detailed, contextually accurate responses. The strengths include enhancing model performance on specific tasks and being easy to implement. The weaknesses include requiring iterative testing and refinement and being model-dependent. This concept is explored in Prompt Engineering for Few-Shot Learning by Schick and Schütze, 2021.
Like, comment, and subscribe.
Multimodal models. Multimodal models extend LLM capabilities to handle multiple data types like text, images, and audio. They work by integrating various data modalities for comprehensive AI applications. For example, Google's Palm E integrates text and visual data for enhanced understanding and interaction. The strengths include providing richer contextual understanding and versatile applications. The weaknesses include increased complexity and computational requirements. This concept is explored in Palm E, an embodied multimodal language model by Agajanyan et al., 2023.
Like, comment, and subscribe.
Multilingual models. Multilingual models are capable of understanding and generating text in multiple languages. They work by being trained on multilingual corpora to capture linguistic patterns across different languages. For example, MBERT and XLMR are multilingual models that support a wide range of languages. The strengths include facilitating cross-lingual understanding and reducing the need for language-specific models. The weaknesses include potentially not performing as well as monolingual models on specific languages. This concept is explored in Cross-Lingual Language Model Pre-Training by Kano et al., 2020.
Like, comment, and subscribe.